CERN has stood out as truly newsworthy once more. The prestigious Lab for Molecular Material Science has declared a fairly remarkable discovery made by their Large Hadron Collider that may likely cause a change in how we interpret the universe. Researchers have reported that these bizarre readings could signal the presence of extraterrestrial life in a parallel universe. In this video, we will examine the newly reported CERN revelation that changes everything. In a recent study with the Large Hadron Collider, CERN researchers observed something odd with a specific type of particle. Particles are the building blocks of all matter and come in various types, which physicists call flavors. Some of these so-called types of particles were very unstable and decayed quickly. The subject of this particular anomaly was the beauty quark, which has a typical lifespan of 1.2 trillionths of a second. It turned out that the quark's decay pattern was drastically different from what researchers had predicted based on the standard model. According to their expectations, when a beauty quark decays, it should be affected by the weak force and transform into what is known as a lepton, which is a set of lighter particles, either an electron or a muon. The standard model predicted a 50-50 chance for the two particles. However, the data from the Large Hadron Collider showed something significantly different. The data revealed that these quarks decayed into muons only 70% as often as they decayed into electrons. This was particularly remarkable because electrons and muons are copies of each other. The only difference is that the muon is much heavier. Still, this difference should not affect the rate of decay. All the forces within the standard model should act on these two particles with equal strength. Since the beauty quark decays through the weak force, both particles should be produced in equal numbers. There is only one possible explanation for this anomaly. A new type of particle, never seen before, is interacting with the process. Some experts have speculated that a new kind of physics could be at play. A new force-carrying particle could mean brand new physics, expanding the standard model and answering many unresolved questions. The possibility of new physics. At present, we have very few ways to test particles, so the standard model remains our best understanding of how the strange world of particles behaves. The standard model is a scientific framework that describes everything we know about the building blocks of the physical world with incredible precision. However, even with this high level of accuracy, physicists are well aware that the model is incomplete. Many pieces of the puzzle are still missing. Of the fundamental forces, the standard model describes three: the electromagnetic force, the strong nuclear force, the weak nuclear force. However, it does not account for gravity or explain the dominant form of matter in the universe, dark matter. During recent experiments, researchers observed an inconsistency in the data that did not align with what is known in the standard model. While it is not uncommon to find unexpected results due to the vast amount of data produced by the LHC, this particular anomaly caught the attention of scientists. They knew they had to investigate further to identify this new phenomenon. What could this new force be? To explain this unusual discovery, scientists have proposed that there might be a new fundamental particle, which they have called Z', a brand new force-carrying particle. Although this force is expected to be extremely weak, since no signs of it had been observed until now, scientists believe it would interact with electrons and muons in different ways. However, the exact nature of its interactions with standard model particles remains a mystery for now. This discovery could mark a turning point in physics. If new force-carrying particles are found, physicists hope this revelation could help unlock long-standing mysteries of the universe, such as the nature of dark matter or the full role of the Higgs boson in shaping our world. Some researchers have even theorized that this unknown force could help achieve one of physics' biggest goals of the past century: the unification of the fundamental forces of nature. The Large Hadron Collider and its work. The Large Hadron Collider (LHC) plays a crucial role in testing these theories. It accelerates beams of particles, especially protons and lead particles, to incredibly high speeds. Proton and lead collisions are typically conducted for 1 month each year. The primary objective of the LHC is to allow physicists to test the predictions of various particle physics theories. Researchers are searching for a vast array of new particles predicted by subatomic theories and measuring the properties of the Higgs boson. Hadrons are subatomic composite particles bound together by the strong force, much like how the electromagnetic force binds atoms and molecules. Commonly recognized hadrons include protons and neutrons. Other hadrons, such as pions and kaons, were first identified during cosmic ray experiments in the late 1940s and early 1950s. The LHC brings two opposing particle beams together so they can collide. These particle collisions result in showers of particles flying in various directions. However, most of these particles have extremely short lifespans, existing only for fractions of a second before decaying into nothingness. By varying the types of particle collisions, researchers can discover new particles. To prevent any data loss, highly sensitive detectors are placed around the collision sites. The LHC generates an enormous amount of data, requiring massive computational resources and human effort to analyze. At CERN, experiments conducted at the LHC produce over 15 petabytes of raw data each year. In 2017, scientists permanently stored more than 200 petabytes of data in CERN's tape libraries. To put this into perspective, 1 petabyte is equivalent to roughly 250,000 movies. The Higgs boson, a groundbreaking discovery. The Higgs boson is an elementary particle associated with the Higgs field. It represents the quantum excitation of this field, similar to how waves ripple across the ocean. The Higgs boson is a unique particle in the zoo of fundamental particles. It does not have the same quantum properties as either matter particles or force-carrying particles like the photon, weak force carriers or strong force carriers. The Higgs boson was discovered at the Large Hadron Collider in a groundbreaking experiment conducted by two large multi-purpose projects, ATLAS and CMS. The discovery was announced on July 4, 2012, at CERN. At the time, the new scalar boson was primarily observed in two rare decay channels, which offered the cleanest signal. The ROT was seen in a couple of photons, which included a simple quantum virtual cycle, and the immediate ROT in a couple of Z bosons, the transporter of the unbiased feeble interaction. The discovery of the Higgs boson at that time might have completed the Standard Model, yet this wasn't the end of exploring this subtle molecule. One of the critical revelations made since 2012 involved confirmation of the ROT of the Higgs. According to researchers, the examination of this elusive particle will expand during the third run of the LHC, especially when the Atom Smasher's high luminosity upgrade is completed in 2029. This will allow the LHC to conduct more collisions, giving scientists more opportunities to detect extraordinary physics, including phenomena beyond the Standard Model. CERN has estimated that as the accelerator is upgraded each year, it will produce 15 million of these particles, compared to 3 million Higgs bosons produced by the LHC in 2017. This might be vital to identifying different types of Higgs bosons. Theories that go beyond the Standard Model of particle physics predict as many as 5 different types of Higgs bosons, which may be produced less frequently than the primary Higgs boson. The magnetic Higgs boson. Even before the upgrades, scientists have already provided strong indications of a magnetic Higgs boson. But what is so important about this Higgs boson? The Higgs field played a crucial and decisive role in the first moments after the universe's birth. It determines the physical nature of the vacuum that fills our spacetime. It is the reason matter and interaction exist as we know them, and it is responsible for the presence of the mass of all known elementary particles. Without the Higgs field, and therefore without the Higgs boson, there would be no atomic elements, no stars, and no life in this universe. The God particle and its significance. Why is the Higgs boson considered the God particle? The Higgs boson's nickname, the God particle, was popularized by the media. The origin of this term is typically linked to Nobel Prize-winning physicist Leon Letterman, who had referred to the Higgs boson in frustration as the goddamn particle because of how difficult it was to detect. According to Business Insider, when Letterman wrote a book on the Higgs boson in the 1990s, he wanted to title it The Goddamn Particle, but the publishers declined and changed it to The God Particle. That was the beginning of a controversial connection between the particle and religion, which still irritates physicists today. Still, it's hard to overstate the importance of the Higgs boson and the Higgs field. Without them, particles wouldn't have mass, meaning there would be no stars, no planets, and no people. Perhaps a small justification for its exaggerated nickname. Why continue studying the Higgs boson? Why do some scientists still study the Higgs boson? Beyond the obvious need to create the most precise description of this new particle, there are two main reasons why researchers continue their study. First, they want to understand how the physical vacuum in which we live was created in the early universe. Second, they want to understand how this vacuum can be made stable. The Higgs field is unique, providing a non-zero expected potential energy to the physical vacuum. Essentially, this has a major impact on our universe. Scientists believe there is a possibility of accessing the state of the energy potential that is responsible for the electromagnetic force, which has infinite range, and the weak force, which acts at very short ranges. To do this, they must study how Higgs bosons interact with each other, requiring the production of Higgs boson pairs. The Higgs boson answered a major question about the origin of mass for all other elementary particles. However, its own mass remains unexplained. No known symmetry in the theory protects this mass, leading to instability. In extreme quantum processes, this instability could theoretically cause the vacuum itself to decay, though fortunately this would happen on timescales far longer than the age of the universe. Still, researchers are searching for additional Higgs-like particles that could indicate the presence of new physics needed to stabilize the Higgs boson mass. These factors motivate the continued collection of more data and, if possible, access to higher collider energies. For this reason, thousands of scientists worldwide remain dedicated to the project, even more than a decade after its discovery. Why did it take so long to discover the Higgs boson? The Higgs boson was proposed in 1964 and discovered in 2012. Science enthusiasts often wonder why it took so long. The Higgs boson is both massive and extremely unstable. To produce such a heavy particle, scientists needed to concentrate a tremendous amount of energy into a small volume, requiring a high-energy collider. Once produced, Higgs particles decay in various ways, and only a small fraction of them can be detected against the background noise. To detect such particles, scientists built the largest and most complex detectors ever. Then, they analyzed billions of proton collision events to extract the Higgs boson signal. Could CERN have opened a dimensional gateway? The question remains: will CERN's projects and discoveries lead to groundbreaking breakthroughs, or could they bring about our ultimate doom? Conspiracy theorists have three popular theories about what CERN is really doing. 1. Opening a gateway to hell. Some believe that CERN's experiments involving subatomic particles moving at the speed of light could open a portal to hell. However, CERN has clarified that its goal in studying antimatter is to better understand matter and mass. 2. The Mandela effect. The Mandela effect describes a phenomenon where many people remember past events differently than they actually occurred. Some conspiracy theorists think CERN's experiments might be shifting our reality, pushing us into an alternate dimension and creating large-scale Mandela effects. 3. Human sacrifices at CERN. In 2016, a video surfaced online allegedly showing a ritualistic sacrifice at CERN. The video appeared to depict cloaked figures on the grounds of CERN, supposedly stabbing a young girl in the chest. According to The Guardian, a CERN spokesperson later dismissed the claims, stating that the ritual was an elaborate prank. Whether a police investigation followed remains unknown. It's no secret that CERN has long been a target of conspiracy theories. So it was no surprise that when scientists resumed operations on July 5, 2022, after 3 years of upgrades and maintenance, wild theories resurfaced online. While science enthusiasts may find these rumors frustrating, it's clear that CERN has no plans to open a portal to hell, the future, or any other dimensions. Meanwhile, beams of particles continue to whiz around the 27 kilometers ring of the world's largest particle accelerator, buried more than 300 meters underground. For over a decade now, the LHC's ability to smash particles together at ultra-high energies has helped humanity explore the uncharted frontiers of physics. A major breakthrough in neutrino detection. The Forward Search experiment, phasor detector at the LHC, has achieved an unexpected milestone. For the first time, it detected high-energy neutrinos produced by a particle collider, identifying 153 events with extremely high certainty. This major breakthrough in particle physics could help scientists expand their understanding of highly interactions in the universe, and unravel the mysteries of stellar fusion and supernovae. Neutrinos are tiny subatomic particles that appear whenever atomic nuclei fuse or break apart. They are produced by cosmic rays, radioactive decay, particle accelerators, and even nuclear reactors on Earth. Even something as simple as a banana emits neutrinos due to the natural radioactivity of potassium in the fruit. However, these massless, chargeless particles are the ultimate cosmic phantoms. Once produced, they rarely interact with matter. About 100 billion neutrinos pass through every square centimeter of our bodies every second, yet we don't feel them.